In this video, I will demonstrate how you can use the Amos graphical user interface to build and test a confirmatory factor analysis. Basically, confirmatory factor analysis is utilized when you have a priori hypotheses about the factor solution and which, the number of factors, and also where the measured variables or indicator variables should load with respect to each factor. So this is an example of a factor analysis that I performed yesterday, and I'm just going to reproduce this analysis currently. So first off, I'm going to clear off this the project, and then I want to widen the space because I want to draw this model out. So I'm going to go to Interface Properties. I'll click on Paper Size, go to A4, and that gives me really a lot more space to work in terms of drawing out my model. So the first thing I want to do is I want to import the data from SPSS into Amos. So I'm going to click on this little box right here for select the data files, and I'll click on file name and then my SPSS data file. So I'm going to click on open, and so now you can see the name of the file appears as well as the total number of cases in the data set. I can, if I want to take a look at the data, I can just click on View Data, and so you can see that here we've got essentially 15 measured variables. Basically, these are survey responses reflecting levels of agreement or disagreement with different survey items. So these items measure prejudice, these measure contact, intergroup anxiety, opposition to inclusion, and intensivity beliefs. So at any rate, now I'll just click on OK, and so now the data file has been imported into Amos, and I can now begin to draw out my model. So first, you can see right here, if I click on this little button, it says variables in the data set. So these are all the variables that was in my SPSS data file. So I want to draw out 15 indicator variables or measured variables to start with. So I could draw out the 15 variables and then draw from there, or I could actually make my life a little bit easier. Just if I draw out one single indicator variable right here, and then I can add a uniqueness. The thing is that every indicator variable that's in your model will have an error term associated with it that's called a uniqueness, and basically the uniqueness reflects the variation in the indicator variable that is not accounted for by the latent factor. So here you can see I've got one indicator variable as well as a uniqueness associated with it. You can see that the uniqueness appears as a circle, so it's basically a latent variable in the model, and you can see that we have an arrow pointing from the uniqueness to the indicator variable, and you can see that the path is set to 1 because one of the requirements of model identification is that all latent variables have a scale of measurement. And so basically we are fixing the measurement scale for the indicator variable in relation to, we're fixing the scale of the latent uniqueness variable in relation to the indicator variable. So you can see right here we've got essentially the beginnings of our model. So I could do this literally redrawing all of these, but if I want to keep things nicely in proportion and so forth, I can make my life a lot easier by doing this number. I can basically say select all objects, and then I can use a little copy machine right here, and I can drag down. So there's item 2 right there. Then there's item 3, item 4, item 5, item 6, item 7, item 8. Remember, we had 15 items. Item 9, item 10, item 11, item 12, and I could still keep drawing this, but I'm just to be consistent with what I had previously at the start of this. I'm just going to copy this and bring this over, and I'll say this is item 13, item 14, and item 15 right here. So now I'll deselect everything, and now what I can do is, if I want to move these uniqueness terms around, I can just click back on this little box right here and just click it around, as you can see right here. So now I'll click this button off, and essentially I can go to my variables list right here, and I can start dragging the variable names into these boxes. So there's the names of each of these variables here. And then we'll add the last three over here. Okay, so there you go. If I wanted to change the size of these, like for instance, to make this a little nicer looking, I could do that. I could right click on Object Properties, and for the size, I could actually just change the font size if I wanted to. Instead of 18, I could put 17, or you know, or something less than that, like 13 here, and you can see it appears in this particular case right here. So I could do that if I want to. Just kind of FYI on that particular issue. So I'm going to leave those alone. I'm not going to spend a lot of time on that, but just to say that those are some, you can kind of clean things up if you want to do that. Another option is if you can add different variable labels. So I could say contact 3. Back here I could say contact 2, and so if I add a label, then it changes what appears here. You don't get the variable name, but you get the label that is given. So there you go. So at any rate, again, that's just kind of illustrating a couple of bells and whistles for the program. Now, I also want to name the uniqueness factors. So I'll right-click here, go to Object Properties, and I have to give each of these a name. So typically, I'll just call it something like U1, and then if I click down here, it clears out, and I can say U2 right here, U3, oops, U4, U5, U6, U7, U8, 9, 10. Okay, so now I've added in the uniqueness. Again, it's not looking very pretty right now, but I'm not really focused on the attractiveness. I just, again, if I want to change the size of these variable names for the uniquenesses, I can certainly do that. There you go. It looks a little nicer there. All right, so next step is to draw out our factors. So I'm going to click on the oval here, and I've got, essentially, this will be my first factor. Just again to make things kind of nice and clean looking, there's my second one, my third one, and my fourth one, and then my fifth one. Keep in mind again that I've got 3 indicator variables per factor, but you could have more than 3. There's no requirement equal numbers of indicators, but you do want to have at least 3 indicator variables per factor. So now I will click off this, and I can right-click, and I'll call this first latent variable, I'll just call this prejudice. The second one I'll call contact. The third one will be, I can say intergroup and anxiety here. Like I said, I can clean that up if I want. This one I'll call opposition to inclusion. And then the last one I'll call intuitivity. Well, I'll just call it intuitivity beliefs. That's a little hard to spell. At any rate, now, so I've got my latent factors, and so the next step is I draw out my proposed relationship. So the idea is that the variation in these indicators of prejudice are explained by a latent variable, prejudice. The same would go for contact, where essentially amount of intergroup contact as a latent variable is explaining variation in these indicators. The same would go for intergroup anxiety, opposition to inclusion, and then we have intensivity beliefs right here. Now, as I said before, one requirement for model identification is that all latent variables have to have a scale. And so generally, if you're when you ask for an unstandardized solution, that means that you're going to need to set the scale of your latent variables in relation to one of the indicators, just like you see right here. So you essentially need to set your paths, at least one of the paths in each set, to 1. And so it's a fairly arbitrary process. Probably makes sense to choose the best indicator to set that path to 1. So, but in this case, I'm just going to arbitrarily set the first item in each set to 1. So I'm going to click on the arrow, click on Object Properties, go to Parameters, and for the regression weight, I'll set it to 1. And then I will click down here and do the same for each one of these. Okay, so now I've fixed the measurement scales of each of these latent variables in relation to the first indicator variable in each set. So when we test the parameters for the unstandardized model, there won't be significance tests for the paths that contain the 1s, but there will be significance tests for the remaining paths. Now, if I want to specify correlated or correlations among the latent variables, I can do that. So you can see right here, I'm just drawing a double-headed arrow, prejudice to each of these variables, as you can see right here, contact to each of these variables, and so forth. And then I also want to include a correlation here. This doesn't look very nice, but basically this is kind of what I'm stuck with through Amos. That's the one downside. I probably, I might be inclined to actually, do things on a smaller scale and shrink everything down and put all 5 of these on the left side, but I didn't actually do that. So now I have basically the model drawn out. The data's been imported into Amos. The next step is go to Analysis Properties and specify those properties. So if you have missing data, then you will want to click Estimate Means and Intercepts. If you don't have missing data, then there's no need to click it. But I believe in my data set I have missing data. I will go to Output, and I can click on Standardized Estimates so that I can get standardized factor loadings in addition to the unstandardized factor loadings. I can click on Squared Multiple Correlations, which will give me the R-square values for each of my indicator variables. And that would tell me the proportion of variation in those indicator variables that's accounted for by the latent factors. I could also ask for other things if I wanted, like tests of normality, modification indices, and so forth, but I'm just going to leave those off for this particular video. So just to kind of show you what happens if you have data that is missing and you don't click on this, I'll just do that really quickly. So the first thing is I need to save this model. So I'm going to say Save As Example Video. And so I've specified everything, and so I'm going to click on Calculate Estimates. And you'll notice it says an error occurred while attempting to fit the models. In order to analyze data with missing observations, you must explicitly estimate means and intercepts. So there you go. There's the error that I was telling you about. So given that there is missing data, I want to click on that, and I'm just going to resave this, and then now click Calculate Estimates, and now it's basically run the model. So if I click on this little toggle right here, it takes me, you can see it says unstandardized estimates. These are all, it looks like a big jumble, and if I want to clean things up and make it a little bit nicer looking, right here, we've got various parameters for our indicator variables and uniquenesses. Really, probably, if we're looking at this model, we really want to only look at the factor loadings and the covariances among the predictors. So if I want to get rid of some of these things, these estimates, and kind of clean things up a little bit, I can just click on the variable and under object properties, under text or visibility, excuse me, and click off the show parameters. And so you can see me removing all of those parameters from the figure. So you can certainly do that. That's just kind of a quick illustration of how you can kind of clean things up. You can do this also over here. If I want to look at the standardized estimates, things are really a lot cleaner over here. Really quickly, the unstandardized estimates, you can see the paths that are fixed to 1 remain at 1, and the remaining paths in the unstandardized solution are essentially unstandardized factor loadings. When we look at these numbers right here for the latent factors, this is basically a mean and the standard deviation, mean set at 0, and standard deviation for each of the latent factors because they're being scaled in relation to the indicator variables. Like I said, if I wanted to remove the visibility of those, I can certainly do that, and as you can see right here. In the unstandardized solution, these would be covariances between the latent factors. So in the unstandardized solution, we have unstandardized factor loadings and essentially the covariances among the latent factors. If I look at the standardized solution, I get standardized factor loadings, which are interpreted very much in line with the structure matrix in the context of exploratory factor analysis, assuming you have essentially a non-complex kind of model, or a pattern matrix if you have like multiple indicators coming, or an indicator associated with multiple factors and that happen to be correlated. But nevertheless, you interpret these largely the same way that you do in the context of exploratory factor analysis. These would be standardized factor loadings. In the context of the standardized estimates, again, these would be all correlations, or interpreted like as Pearson's correlations among the factors. So at any rate, let's take a look at the overall model and the estimates more closely. So we can go to this box right here where it says View Text and click on Model Fit. And so as you can see right here, we've got our fit statistics. We've got the chi-square goodness of fit test, which is basically testing whether there's a significant difference between the model implied variance covariance matrix and the sample covariance matrix. Keep in mind that when we specify a model in SEM, whether it be a path model or a CFA model, it implies a certain covariance structure among the measured or indicator variables. And so we essentially compare that model implied matrix against a sample covariance matrix, and the chi-square test is a test of whether there's a significant difference between the two. So fit is actually reflected by a correspondence between the elements in those two matrices. A lack of fit then would reflect a lack of correspondence or a discrepancy between the two matrices. So if this test right here, the chi-square goodness of fit test, is statistically significant, that would suggest a lack of fit of our model to the data. And in this case, that is the case, that this test is statistically significant. One downside of the chi-square goodness of fit test is that it is impacted by sample size, and given that SEM is a large sample procedure, it's often the case that you can have a fairly minor discrepancy between the two matrices, yet this comes out as statistically significant. So for that reason, we look at other descriptive indices to judge the fit of the model to the data. This indicator right here, this is the ratio of the chi-square value divided by its degrees of freedom. So and values closer to 1, or excuse me, closer to 0 indicate better fit. Basically, the degrees of freedom reflects the amount of parsimony within the model, and so essentially we're sort of adjusting this chi-square value for the model complexity. This particular index is not utilized very often by researchers. I've seen different takes on what constitutes a good fit. I've seen values suggestions that values between 0 and 2 would reflect good fit, values between 0 and 5 reflect good fit. So there's really sort of a disagreement on the thresholds for what constitutes good fit, as well as whether or not we should even be using it all. But even if we were using those two, either of those two thresholds, this would be fairly consistent with a good fit. We have on the next line right here, we've got baseline comparisons. We've got the norm fit index, the Tucker-Lewis index, and the CFI, which is the comparative fit index. Basically, these indices right here compare the fit of your model against a baseline model, which is a null model. The null model assumes that your variables are uncorrelated in your data. And so we're essentially looking at the improvement in fit over a null model. So basically, the NFI is one index of fit, but it's not adjusted for model complexity. The TLI is basically the NFI that's adjusted for model complexity. It's also referred to as the non-normed fit index. And then we also have the CFI, which is a comparative fit index. So basically what we're looking for with these indices right here are values at least above 0.90. Values that fall at 0.95 or greater would be more indicative of sort of an optimal or close-fitting model. Not printed out here, but if we had a complete data set, we would also get the goodness of fit index and the adjusted goodness of fit index. Again, that sort of provides yet another lens for evaluating the fit of the model to the data. And if we were evaluating those, essentially we would be using the same thresholds that I was just mentioning here, which is above 0.90 would be considered good fit or adequate fit. Above 0.95 would be considered more optimal levels of fit. Nevertheless, the program didn't print those out, so we're not going to go any further on that. In the case of the RMSEA, this is called the root mean square error of approximation. And so basically values up to 0.05 would be considered indicative of good fit. Values up to 0.08 would be considered acceptable. Values above that would be suggesting poorer fit of the model to the data. And as you can see right here, we have an RMSEA value of 0.049, which is within that range for close fit of the model to the data. We have right here a 90% confidence interval that's formed around our RMSEA value, and we can test the assumption of close model fit by invoking a null for what constitutes close fit of 0.05. So if 0.05 falls between the lower and the upper bound here, then that would indicate that we have a close model fit to the data, and that is certainly the case in this particular example. The P-close test is basically testing whether our RMSEA value is significantly different from a null close model fit value of 0.05, and so if this is not statistically significant, then that would indicate again that we have close fit of our model to the data. There are various fit statistics to evaluate the overall fit of our model to the data. I've only given you a few of them, but you could think about them as sort of different lenses by which we can look at the fit of our model to the data, at least in a global sense in terms of the overall configuration that we've specified. We also have, if we click under estimates, we get our table of regression weights. These are unstandardized regression weights. Basically, in the context of factor analysis, these are factor loadings, unstandardized factor loadings. And so what we have then is the unstandardized factor loading, the standard error for the factor loadings, the critical ratio, which is a ratio of the estimate to the standard error, and that is being compared against the unit normal distribution, basically the z-table. Rather than having to go into that table, we can just look at the p-values for each of these paths to determine statistical significance. So when we have three asterisks that are presented, that's just basically a p-value that is less than 0.001. You'll also notice in the unstandardized solution that we have the paths that are fixed at 1 as you can see right here. And so there is no significance test for those particular paths, because those paths are essentially setting the measurement scale of the latent variable in relation to one of the indicator variables. So you can see that all the factor loadings that we were testing out, those are all statistically significant. Essentially these values, if we go back and we look at our figure here, if we go to the unstandardized estimates, these are the same values that were present in this particular table right here. With respect to the covariances that you see over here, we can scroll down and you can see the covariances, and so these are the covariances among the latent factors. So these are the covariance estimates, standard errors, critical ratios, and p-values, which allow you to determine what relationships among the latent factors are statistically significant. And it turned out that there was a significant relationship between contact and anxiety, anxiety and opposition inclusion, intentativity beliefs and prejudice, and intentativity beliefs and opposition to inclusion. So these are associated with the unstandardized solution. If we look at the standardized estimates, like I said, these are then essentially standardized regression weights, or you can, using a factor analytic language, these would be standardized factor loadings, and these would be correlations among our latent variables. In a standardized solution, the latent variables are given a variance of 1, and so there is a scale that is assigned to the latent variables, but there is no fixing of paths as we did with respect to the unstandardized solution. So like I said, one of the main assumptions with model identification is that we set the scale of all of our latent variables. So in the context of a standardized solution, the variances of the latent variables are set to 1, and so the scale then is not set in relation to the indicator variables. So going up here, we can see the standardized regression weights. So these are the standardized factor loadings. And then when we scroll down, we can see right here, these are the correlations among the latent variables. So these would be interpreted in the form of Pearson's correlations. I do want to draw your attention. You'll notice that there were a couple of indicator variables with little r's next to them, and that basically reflected a reverse coded item. I had not actually performed the reverse coding, but essentially the way that folks responded, a higher value on that particular item would reflect lower levels of the latent factor. So that's why you have a negative coefficient for a couple of these right here, and the same would go for our standardized estimates right here. So at any rate, if we scroll down a little bit further, you'll see that you get squared multiple correlations, and in this case right here, basically the let's see if I can move this up just a bit here. These are our square values associated with each of our indicator variables. So basically 0.542 would mean that in this context right here, that our belief variable right here, the latent factor, accounts for about 54.2% of the variation in item 3 right here. And you can see I hadn't cleared off those estimates. So these are the R-square values under the standardized solution that you have right here. You can see that in terms of opposition inclusion, 3R, that essentially this latent factor accounts for about 26.9% of the variation in this variable right here. So basically the squared multiple correlations are R-square values and would reflect the proportion of variation in each of the indicator variables that's accounted for by its respective latent factor. Now, I do want to bring out or raise one other point. That is that this is a fairly simple model in that we have pure indicators of each latent factor. But I could theoretically test more complex models. For instance, let's say that I think that this item right here also reflects a certain amount of variation that's accounted for by intergroup anxiety. So I can create a cross-loading, as you see right here, and then test that out. Or, if I want to add in let's say intergroup anxiety also contributing to contact. This is atheoretical, but work with me here. So I could specify those things. I could also, in theory, specify correlations among the uniquenesses themselves. For instance, I had two items that were reverse coded. I had this item right here and this item right here. And so let's say I'm proposing that there's a method effect that may create a correlation between those two items. Well, what I could do, I could actually create that correlated error term. I'm going to quickly select everything and move things over just a shade here, and then deselect, and then I'll add in a correlation between this variable here and 2R right here. So in this case, I can capture a method effect that may explain why this error term and this error term might be somewhat correlated with each other. So then when I run the analysis, you can see I've gotten the analysis run, and looking at the fit, you can see that really the fit statistics were again indicating a good fit to the data. But look at the estimates. And in this particular case, you can see that adding a path from intergroup anxiety to prejudice, that path right here, from here to here, is not statistically significant. So that's actually indicating poor fit. And really that intergroup anxiety to contact was really not a very good idea either, even though it was statistically significant. The downside of that particular approach was that it was completely atheoretical. But nevertheless, the whole point is that you can test more complex CFA models in Amos. You can add complex factor loadings where you have cross loadings where some of the measured variables reflect variation in multiple predictor variables. You can also add in correlated errors. So that pretty well concludes this illustration of confirmatory factor analysis using Amos.